Hi there, this is Dr. Dell, and this is now, I think it's the fourth video we'll have in interlude number 3. It all started with what is the area of the triangle whose sides measure 3, 4, and 6. And as you know, we have a way of using the generalized law of Pythagorean theorem to solve that. That is what I teach in the foundations course. It's this formula right here. And if you don't immediately recognize it, you need to watch the previous videos where I explain that in quite a bit of detail. Now, I talked on the last video about Heron's formula, which kind of, where did it come from and who got the idea for it? Well, it turns out it is a special case of another formula that is called Brahmagupta's formula. Now, I have to tell you, I had never heard of this until I read Dr. Simmons' wonderful book, Pre-Calculus Mathematics in a Nutshell, which we use in tiers 3 and 4 that you know. And this is in the appendix in geometry on page 30, Brahmagupta's formula. And I'm going to tell you a little bit about it. I must tell you, this is the first time I'd ever heard of it was when I read this book. And we, of course, now will discuss this not until tier 4 in our 10-tier system. I don't go into it in tier 3. I think it's just a little too advanced and asking too much, but it really, really is quite interesting. And by the time a student has gained enough mathematical maturity in tier 4, it's time to really talk about it. Now, it turns out that in his proof of this, George Simmons uses the generalized Pythagorean theorem. And he also uses a corrected triangle area formula, both of which I've taught in the foundation course. And he uses those in the proof of this. But here's what Brahmagupta's formula says. Suppose you take a four-sided polygon, a quadrilateral, that has sides measuring A, B, C, and D. And suppose you define the semiperimeter as just half of the perimeter, A plus B plus C plus D. That's the semiperimeter. Then the area of this quadrilateral will be S minus A times S minus B times S minus C times S minus D square root. Now, it turns out that this formula, though, is not true for a general quadrilateral, and you can certainly see why that is with a little thought. In fact, I challenge my students. I assume I'm talking now to somebody that knows some math and is probably a teacher. So what I do is I challenge the students to think why this would not be true in general. And the reason is if you have a quadrilateral, it's not rigid. You can distort it greatly and get any size area you want. Well, not any size, but you can certainly get smaller and smaller areas. This only applies, this formula, is if your quadrilateral is inscribed in a circle. And if that happens, if you inscribe this in a circle, then this formula is true. And George Simmons proves it, and I'm not going to go through the whole proof, but I'll just give you a kind of a hint of how he does it. He draws a diagonal from one, not a diagonal really, it's a line from one vertex to the other of the quadrilateral, and he now has two triangles. And so this triangle has, I'll call this angle 1, and I'll call this angle 2. And I think he calls it N and M, but it doesn't matter. And then he applies the generalized Pythagorean theorem. He knows A and D, and he knows C and B, and this will be length, I'll call it H, and give it a name. And here's what he knows, and we learned this in the foundation course. If you take angle 1 and you add that to angle 2, that'll always be 180 degrees because of the way they're inscribed in a circle. Now, I'm not going to elaborate on that, but actually somebody that takes the foundation course would be able to understand that. And that's basically because angle 2 is half of this. If this is the center, you took the central angle, that's half of that, and angle 1 is half of its central angle. And so when you put them together, you get 180. And the opposite will be true over here. These two will be 180 when they add up. Of course, in general, we know the sum of the angles of a quadrilateral is 360. But it's really critical that these two be supplementary angles. And once you know that, you can do some algebra using the generalized Pythagorean theorem and derive this formula. It's a bit of a mess, but you can do it. He also, during the process of doing that, uses the area formula where the area of this triangle is 1/2 A times D times the sine of angle 1. this area is 1/2 of C times B times the sine of angle 2. It's what we call the corrected area formula we use in the foundation. So really, somebody that's had the foundation course is actually prepared to prove this or to understand his description. And indeed, I found it more enlightening than his discussion of Heron's formula. So if you look down through his proof on page 30, which is in this appendix of the book, you will see that's how he does it, is essentially what I just outlined there was, of course, a bunch of algebra. Now, once you've got this formula, then, of course, if you shrink down, say, D, side D, to 0, you would just have a triangle here, and S minus D would be S, and now you've got Heron's formula as a falls out of that. So maybe this is how Heron found it originally. Maybe he used trigonometry and this fact here to find it. I don't know. That's an open question. Maybe some of you can do some research and let me know if anyone comes across any information on it. I'd be interested in knowing. And who knows, maybe we'll do a video together on it. You can call me by Skype and we can do an interactive discussion of it. And I'm always glad to do that. Sometimes we do that, record them, and then with your permission, we might even share with other people. Now, this also led me then to some further thinking that I'll share with you. And this is what I would do up in Tier 4 with now our better students that are really in Tier 4 and they want more of a challenge. If you have this quadrilateral A, B, C, and D, and of course we know it's flexible, you can move it around, what is the position that would give you the greatest area for the quadrilateral? And indeed, I believe it's when you inscribe it in a circle like this. It's when you move it around to where it's inscribed in a circle. And there's only one circle that'll ever work, as you can easily convince yourself. And so I believe this is the quadrilateral with these 4 sides that would have the maximum area. Any of the others that you move around will have a smaller area, not larger. Now, that's not very difficult to prove. I actually came up with kind of a proof of that to convince me of it, and that's what I challenge my students to do. Then it leads to a bigger question. What if you had multiple sides in a quadrilateral inscribed in a circle? Maybe you had 5 sides or 6 sides. Could you get a similar formula for the area? Well, I don't know. I haven't thought much about it yet, and maybe you could, maybe you couldn't. Certainly it leads me to then think about, if you have a polygon, what's the way to get the maximum area? And inscribing it in a circle seems to be the answer. I don't know if that's always the answer. I suspect that it is. One of the things that it made me think about is what's called the isoperimetric inequality that I would then share with my students along about this time in Tier 4. And again, this would be optional material for them. This is for those students that really are wanting to learn math now and are doing quite well at it and having fun with it. And what it basically says is, if you have a closed curve, a closed line, what's the biggest area that you can make with it? And the answer is a circle. That's something that's mathematicians have proven a long time ago. It's a very interesting problem, but it has practical applications in probably in engineering in many areas. For example, if you take an octagon, or I mean a hexagon in this case, what is and if it's a regular hexagon, what would be the biggest area? Well, pretty clearly it would be if these were all equal angles. That would then be inscribable in a circle, and that would give you the biggest possible hexagon. And maybe honeybees have figured that out through evolution to get the most area and then indeed the most volume in their cones. Who knows? These are all very interesting things that mathematics leads to. As you know, mathematics is the foundation really of modern science and technology. And the better you understand math and the more you learn about it, the better you're going to understand technology and be able to make new discoveries. And that's what this is all about. That's what high school math should be all about, is teaching our students things that they may be able to use as they further themselves go on into science and technology. I must say I do not discuss these things in the foundation because this is beyond what I call practical everyday math, but it's certainly what the kind of things we talk about extensively then in Tiers 3 and Tier 4, and then even the upper tiers. So this is Dr. Dell. I hope you've enjoyed this, and I will see you on some future video, perhaps in the foundation course if you decide to join us for that. Bye-bye.